ever think about what's smaller than the smallest stuff? Like, we all know about protons and neutrons, right?
Yeah, the classic building blocks of matter.
But what if I told you there's a whole world of particles, even more fundamental, more exotic, stranger arrangements than just those three quarks hanging out?
Well, it gets pretty wild when you start thinking about exotic hadrons. These things really push the boundaries.
Exactly. And today we're diving deep into hexaquarks.
Hexaquarks.
6 quarks, way more than the usual 3, and we're going to see why these things are blowing particle physicists' minds. Our guide for this deep dive is an awesome essay, Hexaquarks, Einblicke in die exotische Quantenmaterie.
By Jürgo Schneppat.
Yeah, Schneppat really lays it out there.
Yeah.
But for anyone tuning in who needs a refresher, we got baryons. Those are our proton and neutron guys, 3 quarks each, and then there's mesons, the quark-antiquark pairs. Hexaquarks, as Schneppat points out, are taking us way beyond that comfort zone.
Into uncharted territory.
Totally. So buckle up, folks, because we're about to unpack these hexaquarks. The theory, the potential impact, the hunt to actually find them. It's going to be a wild ride. Okay, let's start with the basics. What exactly do we mean when we say hexaquark?
Well, simplest way to put it, a hexaquark is any particle made up of 6 quarks.
Straightforward enough.
But, and this is where it gets interesting, as Schneppat points out, those 6 quarks could be arranged in a couple of different ways. You could have all 6 bound together super tight, like really close. Or you could have 2 baryons, those 3 quark guys, already color neutral, but they're so attracted to each other that they act like one unit.
So like one big 6 quark blob versus 2 3 quark blobs stuck together.
Exactly. And the force that governs all this, whether it's 6 quarks in a single unit or those baryon pairs, is the strong force described by quantum chromodynamics, QCD.
The glue that holds the universe together, basically.
Pretty much. And quarks have this thing called color charge, kind of like electric charge, but instead of positive and negative, it's red, green, and blue.
The primary colors of the universe.
Yeah, you could think of it that way. And for any particle made of quarks to exist, it has to be color neutral. Schneppat explains that in a hexaquark, you either get that neutrality from a perfect balance of colors among those 6 quarks, or you have those 2 color-neutral baryons I mentioned sticking together.
And I remember Schneppat talks about this hypothetical D2380 particle.
The D2380 Dibaryon, yeah. That's a prime example of what we're talking about. It's thought to be 2 delta baryons bound together. And since each delta is 3 up or down quarks, you end up with a 6-quark system.
Okay, so we've got this 6-quark idea, possibly in different configurations, but why should anyone care? What's the big deal with these hexaquarks?
Well, there are huge implications here. First off, hexaquarks could revolutionize our understanding of QCD. By looking at these exotic arrangements, we're pushing the limits of our knowledge about the strong force, how matter works at the tiniest level.
Like putting our theories to the ultimate test.
Right. And if we find stable hexaquarks, well, Schneppat hints at this, they could form entirely new types of matter.
Stuff we've never seen before.
With crazy properties that could change everything. Imagine room temperature superconductors, or understanding the super hot, dense quark-gluon plasma that existed just after the Big Bang.
Whoa, that's some seriously futuristic stuff.
And Schneppat goes even further, right? He talks about dark matter.
Yeah, that's where it gets really mind-blowing. Some physicists think if stable hexaquarks were around since the beginning, they could be a big part of what makes up dark matter. The stuff we know is out there but can't see.
So hexaquarks could be holding the universe together? That's incredible. But this isn't a brand new idea, right? Where did this whole hexaquark thing start?
Well, the groundwork goes back to the 1960s with Murray Gell-Mann and George Zweig, who proposed the quark model. The idea that all these particles flying around were actually made of even smaller things, quarks.
Breaking it down to the basics. Exactly. Back then, they were focused on 3 quark baryons and quark-antiquark mesons. But QCD, which came later, didn't rule out other combinations.
So physicists started thinking, what if there's more?
Precisely. In the 1970s, they started exploring tetraquarks, pentaquarks, and of course hexaquarks.
The theoretical possibilities were opening up.
But they are mostly theoretical. Then, boom. 2014, researchers at the TÜ Accelerator in Germany announced they'd found something that looked a lot like the D2380 Dibaryon.
The 6-quark guy we talked about earlier.
Yep, and its properties seem to fit that 6-quark bound state, specifically 2 delta baryons stuck together.
A huge moment for hexaquark research.
Massive. And since then, places like CERN have been digging deeper, looking for more evidence of the D2380 and other potential hexaquarks.
So we keep talking about quarks, but for those who aren't particle physics experts, what exactly are these things?
Well, quarks are fundamental particles, the building blocks of hadrons. They have half-integer spin, which makes them fermions, and they're unique because they interact with all four fundamental forces: strong, weak, electromagnetic, and gravitational. But here's the thing. We've never seen a quark on its own.
The infamous confinement.
Yep. They're always bound together inside hadrons, and they have these cool properties. Spin, which is always 1/2 for quarks. Fractional electric charge, either plus 2/3 or minus 1/3 of the elementary charge. And then there's that color charge we talked about. Red, green, or blue.
So spin, fractional charge, and color charge. Got it. But there's more than one type of quark, right? What are those flavors I keep hearing about?
Right. There are 6 flavors. Up, down, strange, charm, bottom, and top.
Yeah.
And each flavor has its own unique properties, like mass. Up and down quarks are the lightest and make up the protons and neutrons in everyday matter.
The stuff we're made of.
Then there's strange, charm, bottom, and top, which are much heavier and usually pop up in high-energy particle collisions.
So a whole family of quarks with different characteristics. And these quarks combine to form those hadrons we mentioned before, baryons and mesons.
Right, baryons have 3 quarks. Protons and neutrons are the famous ones, but there are others like the lambda baryon, delta resonances, and the omega baryon with 3 strange quarks.
And then we have mesons, the quark-antiquark pairs.
Yes, mesons are important because they act as force carriers for the strong interaction between baryons. Some examples are pions, kaons, and the gem meson.
Okay, so we've got our quarks and our hadrons, and all this is governed by QCD, right? The theory of the strong force.
Yep, QCD is the framework that explains how quarks and gluons interact. And a key part of QCD is this concept of color charge. Remember, quarks have red, green, or blue color charge, and antiquarks have the corresponding anticolors.
Like a cosmic color wheel.
Kinda. And for a hadron to be stable, it has to be color neutral. So in baryons, you have one of each color, red, green, and blue, which cancels out to white or color neutral.
Makes sense.
And in mesons, you have a quark and an antiquark with opposite colors, also resulting in color neutrality.
So everything's striving for this color balance.
Right. And this leads to confinement, the fact that we never see quarks by themselves.
They're always stuck together.
Exactly. Because the strong force actually gets stronger as you try to pull quarks apart. Think of it like a rubber band. The more you stretch it, the harder it pulls back. So if you try to separate quarks, you end up creating new quark-antiquark pairs that form new hadrons instead of freeing the original quarks.
They just multiply.
Pretty much. And Schneeppert mentions this other wild thing about the strong force called asymptotic freedom.
Asymptotic freedom, what's that?
It means at very high energies or very small distances, the strong force gets weaker.
So quarks are free inside the hadron where they're super close together.
Exactly. It's this weird duality, strong at large distances, leading to confinement, and weak at small distances, which is asymptotic freedom. And there's a mathematical formula for this, which Schneeppert includes in his essay. It's the strong interaction coupling constant Ridas, which basically measures the strength of the strong force. And the formula shows that ASS decreases as energy increases.
So the math backs up the idea that the strong force acts differently at different energy levels. And within this framework of QCD, we get the possibility for these exotic hadrons, like hexaquarks.
Precisely. QCD doesn't rule out these multi-quark states, and studying them gives us a way to test our understanding of the strong force in new ways.
So what makes hexaquarks so special? Why are they more interesting than, say, tetraquarks or pentaquarks?
Well, with 6 quarks, you have the potential for some really unique properties. For example, the strong force interactions could lead to much higher binding energies, which could make them more stable than other exotic hadrons.
Stable exotic particles, that's a big deal.
Absolutely. Plus, different combinations of quark flavors and colors could give rise to exotic quantum numbers, things we don't see in regular baryons or mesons. And remember that D2380 Dibaryon. It could be a bridge between single hadrons and nuclear matter where lots of baryons interact.
Like a missing link in the particle world.
Kind of. And we can't forget the dark matter possibility.
If stable neutral hexaquarks are out there, they could be a huge part of dark matter.
Exactly. That's a major driving force behind a lot of the research.
So we need a way to tell hexaquarks apart from other hadrons. How do we do that?
Well, the first clue is just the number of quarks. Baryons have 3, mesons have 2, tetraquarks have 4, pentaquarks have 5, and hexaquarks have 6. But the way they're bound together also matters. Baryons and mesons are compact, but exotic hadrons could be more loosely bound, like molecules made of 2 hadrons. And hexaquarks, especially dibaryons, could have longer lifetimes than other exotic hadrons because of how they're bound and the ways they can decay.
So it's not just about counting quarks, it's about how they're arranged and how tightly they're held together.
Absolutely. And back in the 1970s, a physicist named Richard Jaffa predicted the existence of bound Dibaryon states. He even proposed the H-Dibaryon, made of 2 up, 2 down, and 2 strange quarks, which some calculations suggest could be stable.
A balanced mix of the lighter and heavier flavors.
Right. And the theory suggests that these 6 quark states could exist in different ways. They could be compact, with all 6 quarks in a tight bundle, or they could be like molecules, with 2 baryons held together by residual strong forces. To figure this out, physicists use the Schrödinger equation, which describes the quantum states of particles. By plugging in the right potential energy function, they can see if a bound state forms and what its properties are.
So they're using math to predict how these quarks would behave.
Exactly. And on the experimental side, there have been some big efforts to find hexaquarks. The Cosmology experiment in Germany, where the D2380 was discovered, is one of the key players. The LHC at CERN, famous for finding the Higgs boson, has also been searching for exotic hadrons, including hexaquarks. And then there's JPARC in Japan, which has been specifically looking for the H-Dibaryon.
So different experiments with different approaches.
And they use various techniques to detect these particles. One is spectroscopy of resonances, which looks for peaks in the energy distribution of particles produced in collisions. The D2380 was discovered this way.
Like a fingerprint of a new particle.
Right. Another technique is tracking particles and looking at their decay patterns. If a particle lives longer than expected or decays in a weird way, it could be an exotic hadron. And then there are heavy ion collisions, which create quark-gluon plasma, the super hot, dense stuff that existed in the early universe. By studying this plasma, physicists might be able to see signs of hexaquarks.
Wow, it sounds like finding these hexaquarks is a real challenge.
It is. There are a lot of hurdles. They could decay too quickly to be detected, or they could be so stable that they barely interact with our detectors. And their decay patterns could be super complex, making it hard to figure out where they came from. Plus, our detectors are optimized for finding regular hadrons, so we might be missing the faint signals of hexaquarks.
It's like looking for a needle in a haystack.
Exactly. And we might need even more powerful accelerators to produce some types of hexaquarks.
So it's a tough job, but the discovery of the D2380 gives us hope.
Definitely. And with new experiments and technologies on the horizon, we're bound to learn more about these fascinating particles.
Now, in his essay, Schneepat doesn't just talk about fundamental physics, he also explores some really cool potential applications of hexaquarks, especially in quantum technology. That's a bit unexpected.
It is, but it shows how far-reaching this research could be. For example, Schneepat suggests that hexaquarks might be used as qubits in quantum computers.
Whoa, hold on. Quantum computers powered by hexaquarks? How would that even work?
Well, because of their complex structure and strong interactions, hexaquarks might be more stable and resistant to noise than other types of qubits. This means they could hold their quantum state for longer, which is crucial for doing complex calculations.
So they'd be like super-powered qubits.
And because they have 6 quarks, you could potentially encode information in more complex ways, maybe even creating higher dimensional qubits.
So more information per qubit. That's wild.
And Schneepat also talks about using hexaquarks for quantum communication. If we can entangle them, meaning link their quantum states even when they're far apart, we could have super secure communication channels. They could even be used as quantum repeaters, boosting the signal over long distances.
So hexaquarks could revolutionize how we send and receive information.
And it doesn't stop there. They could also have a huge impact on material science, particularly superconductors.
Okay, how so?
Well, if stable hexaquarks exist in dense matter, they could act as new types of quasi-particles, changing how electrons interact. This could affect how Cooper pairs, the electron pairs responsible for superconductivity, form. And maybe, just maybe, we can create room temperature superconductors.
That would be a game changer.
Right. And Schneepat even speculates that hexaquarks could stabilize other forms of exotic matter, leading to new materials with crazy properties.
So new materials, new technology, it's all connected.
And it gets even wilder. Schneepat talks about hexaquarks as potential energy sources.
Hexaquark power plants. Now you're just messing with me.
Well, it's still very speculative. But he suggests that hexaquarks could catalyze nuclear fusion, making it more efficient.
So cleaner, more powerful energy.
And if stable hexaquarks are abundant enough, they might even be a new energy source themselves.
We could be powered by 6 quark particles.
Imagine that. And Schneepat also discusses the potential for hexaquark-based sensors.
Okay, what could those detect?
Well, their strong interactions could make them incredibly sensitive to things like tiny changes in the quantum vacuum, maybe even dark matter or gravitational waves, and they could be used for ultra-precise measurements of gravity, maybe even in space missions.
So hexaquarks could help us understand the universe in completely new ways.
And that's just scratching the surface. It's clear that hexaquarks have the potential to be a game changer in quantum technology, from computing and communication to materials and energy.
It's amazing to think how something so tiny could have such a big impact.
It really is. Now, let's shift gears and talk about the cosmological implications of hexaquarks. Could they play a significant role in the universe as a whole?
We touched on the dark matter connection earlier, but is there more to it?
Well, Schneepat really dives into that idea. He explains that the Dibaryon, that 6-quark particle with 2 up, 2 down, and 2 strange quarks, could be a prime candidate for dark matter. Because it would be electrically neutral, it wouldn't interact with light, and it would mostly interact through gravity, which is exactly what we see with dark matter. And if it interacts weakly with regular matter, that would explain why we haven't detected it directly yet.
So it's a perfect fit for what we know about dark matter.
But the big question is whether it's stable enough to have lasted since the early universe.
Right. It has to have survived billions of years.
And there are experiments trying to find evidence of hexaquark dark matter. Some are looking for direct interactions with atomic nuclei in underground detectors, while others are looking for indirect evidence through its gravitational effects on galaxies and other cosmic structures.
So the hunt is on.
Absolutely. And Schneepat also explores the possibility of hexaquarks existing in neutron stars.
Those super dense remnants of dead stars.
Right. If stable hexaquarks exist, they could be a major part of the exotic quark matter thought to be inside neutron stars. This could affect the star's stability, size, and other observable properties. We might even need to modify our theories of neutron star structure to account for hexaquark matter.
So hexaquarks could be shaping the hearts of the densest objects in the universe.
And Schneepat even suggests that they could exist as remnants in the quark gluon plasma created in heavy ion collisions, those experiments that recreate the conditions of the early universe.
So we might be making hexaquarks right here on Earth.
And by studying how this plasma behaves, we could learn more about hexaquarks and their role in the early universe.
It's amazing to think how these tiny particles connect to such huge cosmic phenomena.
It is. And then there's the really wild idea of hexaquark condensates.
Condensates? What are those?
Well, it's the idea that in super dense regions of the universe, stable hexaquarks might clump together to form macroscopic objects, like new types of stars or planets.
Entirely new celestial bodies made of hexaquarks.
It's mind-blowing, right? And if this hexaquark matter exists, it could have huge implications for how galaxies form, how the universe evolves, and we might even need to rethink our theories of gravity.
It really challenges our understanding of what's out there in the cosmos.
It does. And while it's still very speculative, the possibility of hexaquark condensates shows just how fascinating and far-reaching this research is.
It's clear that hexaquarks have the potential to change our view of the universe, but there are still a lot of unanswered questions. In the final part of his essay, Schneepat talks about the theoretical challenges and the big mysteries that remain. Why are these hexaquarks so hard to find and understand?
Well, as we've discussed, the strong force itself is a major hurdle. It binds quarks together so tightly that it's incredibly hard to isolate them and study them individually. Plus, hexaquarks might be very similar to regular hadrons, making their signals hard to pick out. Their lifetimes could also be a problem, either decaying too quickly or living so long that they're invisible to our detectors, and our current experimental setups might not be sensitive enough to detect them. We might need entirely new approaches to really crack the hexaquark code.
So the very thing that makes them interesting also makes them elusive.
Precisely. And there are still some big unknowns about QCD itself that complicate things. For example, we're not exactly sure how quarks are bound together in exotic hadrons like hexaquarks. Are they tightly packed or more loosely bound like molecules? And what are the rules governing their stability and decay? We need to refine our theoretical models to answer these questions.
So we need both better experiments and better theories to solve the hexaquark puzzle.
Absolutely. But there's a lot of optimism about the future of hexaquark research. We have new, more powerful accelerators on the horizon that will allow us to create more of these exotic particles. We're developing new detector technologies that will be more sensitive to their signals. And theorists are making progress in modeling the strong force and predicting the properties of hexaquarks.
So it's a race on both fronts, experimental and theoretical.
And we're learning a lot from astrophysical observations as well. By studying things like dark matter distribution, the cosmic microwave background radiation, and the behavior of neutron stars, we can get indirect clues about the existence and properties of hexaquarks.
So it's a multi-pronged approach to uncover the secrets of these fascinating particles.
And Schneepeck concludes his essay by highlighting the key questions that will guide the next phase of hexaquark research. Do stable hexaquarks really exist? What are the best ways to detect them? And what role do they play in the grand scheme of the universe? These are the big mysteries that will drive the field forward.
It's exciting to be on the cusp of such groundbreaking discoveries.
It really is. And it all started with Schneepeck's insightful essay, which has given us a fantastic overview of this cutting-edge field.
So there you have it, folks, our deep dive into the world of hexaquarks, guided by the brilliant insights of Yurgo Schneepeck. We've journeyed from the tiniest particles to the largest structures in the universe, exploring the fundamental nature of matter, the mysteries of dark matter, the potential for revolutionary technologies, and the ongoing quest to understand our place in the cosmos.
And while we've only scratched the surface, it's clear that hexaquarks have the potential to reshape our understanding of the universe in profound ways.
These elusive six-quark particles could hold the key to unlocking some of the biggest secrets in physics. It's a journey of discovery that's just beginning, and who knows what incredible revelations await us in the years to come. Thanks for joining us on this deep dive, and be sure to check out Yurgo Schneepeck's essay, Hexaquarks, Einblicke in die exotische Quantenmaterie, for an even deeper exploration of this fascinating topic.
It's a must-read for anyone interested in the cutting edge of particle physics and cosmology.
Until next time, keep those minds curious and keep exploring the wonders of the universe.
We'll see you on the next deep dive.